Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today I'm going to make a video that I want to make, and that is how mathematics is the key to the universe. Now, while I have not studied mathematics since I was in school, this has been a great refresher doing debunks in the flat earth community. The reason for that is that I'm using a lot of trigonometry and mathematics and curve calculators and such, and I thought that I would go over that real quick. It's a good refresher for me. It may be a good refresher for you. Now, something that I was particularly interested in and wanted to use as a method of teaching this in this series is the mathematics of the ancient Greeks. For example, by observations of the half moon, we were able to tell the distance from the Earth to the sun in terms of the distance from the Earth to the moon. By looking at a total solar eclipse, we could get a ratio of the diameter of the sun to the diameter of the moon. By looking at a total lunar eclipse, we not only could get an idea of the ratio of the diameter of the sun to the diameter of the Earth, we could get the ratio of the diameter of the moon to the diameter of the Earth. By observing the full moon, we could get the ratio of the distance from the Earth to the moon in terms of the diameter of the moon. And finally, by just putting a stick in the ground and measuring a shadow, we could put numbers on all of these values. Now, that's where we're going to go in the future of this series, but today what I want to do is go over some of the basic mathematics that we're going to be using. So let's cue up the music and come back and learn about sine, cosine, and tangent. Now on the board behind me, we have the mathematics that we're going to cover this episode. What I'm going to do is I'm going to talk about sine, cosine, and tangent, and then I'm going to use an example that we commonly run into using sine and cosine. Now, many of us learned in school about our old friend, the 3, 4, 5 triangle. We all know that this is a right triangle. There's the right angle right there. And we're going to have a look at this angle right here, angle alpha. Now, what is the sine, the cosine, and the tangent for angle alpha? Well, first of all, what is sine? It's the opposite side, opposite of the angle, over the hypotenuse. So our sine will be 3 over 5, or 0.6. How about the cosine? Well, it's adjacent over the hypotenuse. So it would be 4 over 5, or 0.8. And finally, what's the tangent? The tangent is a combination of the two. It's the opposite over the adjacent, so 3 over 4. Now, for those of you that are curious, that works out to be about a 37-degree angle, angle alpha. But there's something that's kind of interesting that you might want to look at. Look at sine over cosine. 0.6 over 0.8. also equals 0.75 because the tangent is the sine over the cosine, and we're going to learn why that's important and how that comes about here in a moment. Now, this very superficial treatment of sine and cosine works fine for what they call acute angles, angles less than 90 degrees. Okay, so let's have a look at something that's a little more complicated. What about this triangle right here? What's the adjacent side? What's the opposite side? What's the hypotenuse, for that matter, for this angle right there? All right, so let's introduce something called the unit circle. Now, the unit circle is on an x-axis and a y-axis, and it's centered at 0.00. Now, the radius of that circle is 1 unit. That's why they call it a unit circle. Now, the formula for that circle is our old friend, the Pythagorean theorem. X squared plus y squared equals 1 squared. That'll come in handy a little bit later. So let's go ahead and have a look at a point right here. So there's a point on the circle. Now, what's the coordinate of that point? Well, the coordinate of the point is rise over run. So the rise will be on the y-axis, and it'll be right there. The run will be on the x-axis, and it'll be down here. So our coordinate would be y, x. Make sense? Rise over run. Now what about the sine and the cosine of that angle right there? Well, the sine is the opposite over the hypotenuse, right? We know that the hypotenuse is 1, so the opposite is the sine of that angle. So instead of using yx here, we could also say sine. How about the cosine? Well, that's the area along the x-axis over the hypotenuse. The hypotenuse is 1. The cosine is the same as the x-coordinate. So all we have to do is put in cosine right there. And that is the coordinate of that point. Now remember when we talked about this over here where it's sine over cosine equals tangent? Well, that's where it comes from. Tangent is opposite over adjacent. The opposite is the sine. The adjacent is the cosine. So tangent is sine over cosine. And we demonstrated that right over here with the actual numbers. Now the one thing that I didn't like in math was the instructor sitting up there and writing all this nonsense on the board and then going on to the next subject. Let's go ahead and put this into practical use. Let's look at a couple of problems that we see in home science, flat earth debunking all the time. These are questions that come up. Let's go ahead and have a look. Okay, so here we have the Earth. It's a sphere and it rotates once in 24 hours. Given the diameter of 24,901 miles, that means that it rotates at the equator at 1,038 miles an hour. Well, how about up here where I live at 45 degrees north? What's the rotational speed up there? Well, let's go back to the unit circle and have a look. So let's go back to our coordinate system. Starting to look familiar? So we've got a coordinate system here. And all we do is we draw an angle between the equator and 45 degrees north. So that's a 45 degree angle right there. Now, what exactly determines your rotational speed in miles per hour? So here's the formula for that. So the rotational speed is 2 pi times the radius of the Earth divided by 24 hours. This gives us the circumference. We divide it into 24 hours, which is the rotational period of the Earth, and that gives us a miles per hour, and it works out to 1,038. Easy peasy. But what about up at 45 degrees? Think about it for a second. This is the radius of the Earth. Up here, that is the rotational radius at 45 degrees north. So what would that point be right there on the edge of the circle? That point would be sine 45, cosine 45. Now we learned that in our discussion. Well, what would the rotational speed at 45 north be? Well, just like down here, it'll be 2 pi times the radius at 45 over 24 hours. 2 is the same in both. Pi is the same in both. The only thing different is the radius of the Earth at the equator and the radius of the Earth at 45 degrees. Now, what's the radius at 45 degrees? It's right here. And that, ladies and gents, is the cosine of 45 degrees. So we take the rotational speed at the equator times the cosine of 45 equals the rotational speed at 45 degrees north. Pretty simple. Now the next one's a little bit trickier, and this is something that you hear in the flat earth all the time, so I thought I'd address it real quick. Now one thing that we hear in the flat earth all the time is that earth curve is 8 inches per mile squared. Well, how would you test that? Now this is often put in the context of aircraft. Now if an airplane flies 600 nautical miles, how much drop would there be in 600 nautical miles? And just to make it interesting, because even though airplanes fly in nautical miles, we want the drop in miles. The radius of the Earth is 3959 miles, and 1 degree is 60 nautical miles. Now the reason that I'm using nautical miles for 1 degree rather than 69 miles is that the problem is put up as 600 nautical miles, and it makes the math a little easier. We only need that to determine one thing, and after that we can get our answer very nicely in miles. So let's go ahead and do this real quick. Now, what's the best way to do this? One of the tenets of living on a sphere is the ground goes down in every direction away from you. So essentially you're on the top of a sphere. So let's have this be our starting point right up here, right at the very top of the sphere. And then we're going to go down 600 nautical miles. And we're going to go to this point right here. There's an angle formed there. Now, how much is this part of the angle right here? Well, it's 600 divided by 60, 10 degrees. Okay? How much is this part of the angle right here? Well, if this total is 90 and that's 10, that means that's 80 degrees. So far, so good. Now, the reason that I wanted to use 80 degrees rather than try and calculate it the other way is it's a little bit more visually appealing and straightforward. Now, what is the drop between here and here? Let's go ahead and have a look at that. The drop is going to be the distance down from a tangent line right here, which is a horizontal line, me looking straight out 90 degrees from where my feet are. And we're going to go down to here, and that is our drop. Everybody with me so far? Well, how do we figure out what that is? Well, that should be pretty straightforward from our conversation. What's this point? This point is the sine of 80 degrees times the radius of the Earth. All right, that's how long that distance is right there. Now to find the amount of drop, it's a rather straightforward thing. This distance right here down to the center of the Earth is the sine of 80 degrees times 3959. The difference right here is 3959 minus the distance here, which is the sine of 80 degrees times 3959. Pretty straightforward. Let me go ahead and write that out real quick. So 3959, which is the radius of the Earth, minus 3959 times the sine of 80 degrees. How much does that come out to? Let's see what I've got here. All right, so let's do the math. What's that work out to be? $60.17 miles. That is the drop from our horizontal down to that spot on the Earth. Now, while we're at it, let's go ahead and just compare this real quick to the old 8 inches per mile squared number. So the actual number is 60.17 miles. That's what it is. If you do the 8 inches per mile squared for 600 miles, that's because the 8 inches per mile squared is a surveying shortcut and it's designed to be used over short distances. The only reason that we had the nautical miles is because it was convenient for 600 nautical miles divided by 60 nautical miles per degree. we got our 10 degrees. That's really all we needed that for. So there's two common problems that we use trigonometry to solve in debunking and everyday life. Now in our next episode, what I want to do is I want to talk about the concept of tangent. And the specific example that I want to use is how Al-Biruni found the height of a mountain in his efforts to measure the radius of the Earth. He used tangents. And we'll go through that real quick. It's a very elegant and easy to understand concept, but it's fun to do. Now our next episode will be on Tuesday when we start our Trig on Tuesdays series. And not only are we going to look at the Al-Biruni calculations for finding the radius of the Earth, we're going to look at the curve calculator, how to calculate great circle courses, find the shortest distance between any 2 points on Earth. And we're also going to look at the mathematics of the ancient Greeks as we talked about in the introduction. By the way, for those of you that are following along and are curious as to what the rotational speed of the Earth at 45 degrees north is, if you want to check your answers, here it is. It's just shy of 734 miles per hour. So until then, this is Bob the Science Guy signing out from Northern Michigan. And remember, mathematics is not scary. It's a lot of fun when you understand just the very basics of it, and it is the language of science, but we're going to try and make it fun. So take care, guys.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Bob, the Science